Last class, we talked about qualitative data, which was categorical data. So when I took a sample from you guys to use in our notes, I asked you your favorite elective, which was a categorical answer, which then we displayed in different methods. Today we're going to be looking at quantitative data, which means the questions we're going to be asking and studying are numerical in their answer. So we're going to be looking at numerical data and how there are different displays that we can use when we get numerical data. So let's take a quick little sample from the class. I need you to think about your closet and think about how many pairs of shoes you own. And if you don't exactly know, that's fine. Just take a guess of how many shoes you own. We're going to start at the back. Xander, how many shoes do you own? No, pairs of shoes. Okay. Great question. Pairs of shoes. All right. Okay, we're going to go around and take everybody's answer. We have this data from class. We've got everybody's responses. Just as a quick note, because we're going to need this later, how many responses did we have? Total? 24. Just keep that in mind for later, because generally we need to know that. Okay. Questions you always want to make sure you're answering or knowledgeable of as you're taking surveys is what is the variable we are measuring. Clearly we are measuring the number of pairs of shoes. Is that variable qualitative or quantitative? Because I asked you a number of shoes. Nice. Is it discrete or continuous? Continuous. No. What's your final answer? It is discrete. Here's why. Can you have half a pair of shoes? Okay, should you have half a pair of shoes? No. So if we can't have like halves or parts or 0.25s, it's discrete. You will have a pair of shoes or you won't have a pair of shoes. I know you could lose one, but then like you're not wearing that pair of shoes, so you don't have it anymore. That's what I'm saying. Okay. First things first, and the first way we're going to organize this information is into a dot plot. We had seen this before. The dot plot we did like one of the first days of class where we're just going to take all of the individual data points and put little dots above where they would go. So for the first response we had 7, which is about here. And then we had 6, which is right before it. And then 15. And then 9. And then 15. You see how this works? Okay. All right, so here's our display of this data. Immediately we've taken the raw data, which is just all of your general responses, and we put it in this graphical display, which makes it a little bit easier to see where groups of common numbers are and all of that good stuff. However, we want to start categorizing and organizing this data in a different way. So instead of looking at all of the individual responses we had, because we had, if we count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 different responses. If we just did this with a bar chart from last time, you'd need 17 rectangles. And that's kind of annoying, right? So instead, with this quantitative data, we can group things into what are called classes. When we're working with a class, we determine a width of our class, and for us, we're going to do 5. So anybody who responded between 1 and 5 pairs of shoes, we're going to count up and put in one solid group together, into a class together. So if we look through our data and start to tally each of these different classes, I would do the following. The first response was 7, and then was 6, and then was 15, and then we had 9, and 15, and 23. Do y'all see how this works? We're going to tally up all of the frequencies of these particular classes from our raw data. Now that we have all of our tallies for this data, we can do frequency. Last time we learned frequency was just like the number of times this appeared. So our frequency for the first class was 3, and then 9, and then 5, 3, 3, 0, and 1. Last time also we learned how to show relative frequency, which was the proportion or percentage this response had out of all of our responses. So 3 of our 24 responses came in the class 1 to 5. So we would calculate 3 divided by 24. But this moment, I'm going to have us practice our Excel skills. So in Excel, to answer what is the relative frequency, what I want you to do is type in all of these numbers. So you'll go 3, enter 9, enter 5, enter 3, enter 3, enter 0, enter 1, enter. And I want you to write a formula that will do the relative frequency of each row. In using our Excel to do the cell divided by 24 and copying that formula all the way down, we should have gotten the following values. This relative frequency for 3 is 0.125, then 0.375, and then 0.208, and then we're back at 3, so that's 125, and then 0, and then 0.042. Is that what we got? Yes. Yay! Excel is a very powerful calculator. Both qualitative and quantitative data can be represented with frequency and relative frequency tables. However, quantitative data is no longer going to be shown in a bar graph, especially when we're using classes. Instead, we are now going to display them in what's called a histogram. It looks like a bar graph, but it is technically different. A histogram this time is going to have the bars touching because we are showing multiple numbers in each rectangle. And immediately after finishing the 1 to 5 rectangle, the 6 to 10 rectangle takes over. So we want to show that there's no break in our data, in our number line, if you will. So all of our rectangles need to be touching. You'll also notice that I didn't put an x-axis down here because I want us to put the class widths correctly on the x-axis. So what we would do is we would start at 1 and go to 5. That's our first class. And then we have 10, and then we have 15, and then we have 20, and then we have 25, and we have 30, and this is just going to indicate the end of 30 plus. So again, I'm not centering my rectangle on this response anymore because this is a histogram with class widths of 5. So I make my widths of these 5. On Excel, whenever you're making a histogram, which is one of the options, it writes your class width in interval notation. So this would say bracket 1, comma 5 bracket. This would say 5 with a parentheses, comma 10, and on, because we included 5 in the first class. But now that we have this frequency diagram ready to roll, because it says frequency on the side, it could have said relative frequency. We could have used the same one, but we just did frequency. We count up the number of responses in that first class. This is why I took a picture of this, so I could see both at the same time. Our first class had how many in it? 3. So our first class, which has a width of 5, so all of the responses from 1 to 5, we had 3 tally marks. From 6 to 10, we had 9. Y'all see how this works? From 11 to 15, we had 5. From 16 to 20, we had 3. 21 to 25, we had 3. 26 to 30, we had none. And our 30 plus had 1. So a potential problem with a histogram, while they give us really good information, we can see where the highest frequency is, all this stuff. If I were to ask you a question, is there somebody who responded with the number 11? Does somebody have 11 pairs of shoes? Yes. Why are you saying yes? Okay, you don't have the raw data. All I'm giving you is what's on the screen right now, which is just the histogram. Could you confidently tell me somebody had 11 shoes? No, because we only have a range of numbers. So this display, while very helpful for summarizing data, we lose the raw data unless you're provided with the table as well. So a way that we can get around that is using the classic stem and leaf plot. Have y'all heard of this before? So a stem and leaf plot is a display of data where you can still see the raw data, where we're going to, on one side, called the stem, put like the tens digit. And on this side, put the ones digit. Those are the leaves. So a stem and leaf plot will then allow me to see the shape of this data, also keeping the number of values of our classes. Now we split our classes by 5, so what we're going to do here, sorry, the second example we're splitting it by class with, this one we're just doing it by decade for lack of a better word. So I want you to put the following, I want you to put 0 and then 1 and then 2 and then 3 and then we will need a 4 because we went all the way to 4. Now, we are going to display our pairs of shoes lining up the raw data on this table, meaning, what is the smallest number in our raw data table? 1. So we're going to put a 1 right here. This number represents 0 in the 10 spot, a 1 in the 1 spot. So that's the number 1. What's the next smallest number on my list? 4. So we would put a 4 right here. Our next smallest number is 5, and then 6, and then 6, and then 7. Did I miss one? And then, oh, there's another 7. And then a 9. Did I miss anybody? If we're looking at our raw data? There's 3 6s? Ah.
There's an 8 before a 9.
Ah. Okay, this is hard. I don't have the data table in front of me because I had to scroll down. Okay, so what we have shown is how many responses, the frequency of the responses that were between 0 and 10, less than 10. Ah. Thank you so much. Fix my mistakes. Okay, I'm going to do better on the 10 spot. So if I'm looking through our data, look through our data, Miss Quigley. What's the smallest number that has 2 digits that starts with a 1, essentially? 10. And then what's the next number? 11. And then 12. There's a 13. 15. 15. 18. Is that it? Nice. We go to the 2s. We're getting any of the numbers in the 20s. We have 2 20s. There's 3 7s, yeah. 20 and 20, and then 23 and 23. Nope. Are there 2 23s or am I blind? I'm blind. 2 25s. Okay, did I miss anything this time? There's none in the 30s. And shout out to the 40. Thank you for your honesty. I bet you some people are going to go home, count their closet, and be like, oh, I said the wrong number. I actually have blank shoes. It's okay. So now, we've displayed this data. We can still see that there is a higher frequency, just like our histogram showed us. There's a higher frequency of people who have shoes in these lower numbers. That's what both of them show me. These 2 have more than these 2. And definitely more than these 2. And that is displayed here as well, except that I could now ask you, did somebody say they have 11 shoes? And you can tell me, yeah, here's the number 11 out of the data. So you still keep the raw data in a stem and leaf plot, which you lose in a histogram. So there's trade-offs for the way that you want to display this data. But a big question in statistics, especially when we're graphically displaying data, is for me to ask you, what is the shape of this data? Now, I've not told you the names of any of the shapes because they're very well named. Can you tell me, don't mark on your paper because I'm going to erase this and I know you can't erase it. If I were to do this and show you the shape of this data, how would you describe it? High, low. Okay, give me some more words. They don't have to be perfect math words. Tell me some more words. It goes up, then it goes down. Where is the uppest up part? I'm thinking more like left, middle, right. Left. Is there stuff that trails off one direction? Yeah, where does it trail off? To the right. So here's some things we noticed. We noticed that there is a bump in this data. That's good to notice. So there's a highest frequency moment. We noticed the highest frequency moment was not in the middle, that it was on the left. And we noticed that things trail off to the right. That allows me to then say that this data has been skewed to the right. We have a tail on our bump that extends further to the right than it does to the left. And we see that our highest frequency is no longer in the center, it's off to one side, and it's skewed to the right. A good question might be, how do you tell this from the stem and leaf plot? Because I had drawn that image on, or the little bump on this guy. They're sideways, and I can't turn my TV to show you this, but if you turn your paper sideways, you can still see that there's a bump more to the left side with a trail going to the right. So we can still use the stem and leaf plot to tell me the shape of the data. Make sense? Okay, we're going to leave the shoes alone for a bit. We're going to talk about the same displays of data, maybe in a different way that I had attempted to do the first time. So again, we're going to make a stem and leaf plot to display the data in this table. The following data represents the ages of the presidents of the United States from George Washington through Joe Biden on their first days in office. What's nice about this data that our shoe data was not is that this is sorted from least to greatest. Y'all see how it starts least here and then goes to greatest? That'll make this way easier instead of me missing numbers because I was looking all over our data tables. Okay, we're going to make a stem and leaf plot and describe the shape of this data. Since we noticed that the tens digits are close together, we only have ages in the 40s, 50s, 60s, and 70s, but we have a lot of numbers that need to be put on our stem and leaf plot. What we can do is we can allow these to be used with class widths to basically separate the 40s into two groups, the 50s into two groups, 60s into two groups, and 70s into two groups. So we're going to take the lower part of the 40s and the upper part of the 40s as one class, and on and on. So we would say something like this. All right, here's our stems. We will do the lower 40s, the lower 50s and upper 50s, the lower 60s and upper 60s, the lower 70s and the upper 70s. Now we need to take all of the numbers from our data table and display them on the stem and leaf plot. Because again, just looking at these numbers the way they're given to me, I can make no conclusions. So let's get started. Again, because these are in number order, it's going to be very easy for me to split them at the lower part of the decade and the upper part of the decade, which would mean that we have 42 and 43 on our first row, 46, 46, 47, 47, 48, 49, 49 on our next row. 50 through 54 will be the next one. So we have 50, 50, 51, 51, 51, 51, 52, 52, 54, 54, 54, 54, 54. Our next row, so the next stem would be all of the upper 50s. 55, 55, 55, 55, 56, 56, 56. That's enough of those. 57, 57, 57, 57, 58. Whew. Did I miss any this time? Okay. Taking silence as yes. Then we go to the lower 60s. So we have 60. 3 presidents were 61, 62, 64, 64. 65, 68, 69, 70, and 78. Here's why doing it like this would be more helpful for displaying this data in a stem and leaf plot. If we had only done one row for 5, would you have been able to get all those numbers on this paper? Me neither. My handwriting's not that small. So we can split it by some class widths that maybe make the information more digestible and display all of the data. Now we still want to describe the shape of this data. If we're describing the shape of the data, I always turn my stem and leaf plot sideways. And if we're looking at this shape, how would you describe it?
It's like a middle.
So the middle, if we're going from 40 to 70, the middle will be right here.
Yeah.
Yeah, that's the middle.
But is our highest frequency actually in the middle, or isn't it here?
No, it's the beginning.
So we have a peak on the left, and we're trailing which direction? So how would you describe the shape? Skewed to the right. Nice. So the skewedness goes in the direction of the tail. I will say this is a pretty normal looking stem and leaf plot, but occasionally you'd see some where it's representing decimals. So the stem is the ones and the leaves are the decimals, or maybe the stems are hundreds and tens and then the leaves are the ones. So a lot of times you'll be asked for a key to your stem and leaf plot, or you'd be given one. And this is what a key would look like, where you say, if you see 4, line 2, that's 42. You can use these to do like 4.2, but you just have to make sure your key is displaying how to read your stem and leaf plot. The last type of graph that we're going to explore that is more specifically for quantitative as opposed to qualitative data brings up the idea of cumulative frequency and cumulative relative frequency, which are called an ogive when you graph them. Ogive. So the data in table 12 represent the total fine, including late penalties in dollars for a simple random sample of 50 parking and camera violations in the city of New York. You're going to use the frequency and relative frequency distribution table to create a cumulative frequency and a cumulative relative frequency table of the data. Now, I've done the hardest part of this one for you because I determined the classes. I looked at my super unorganized data and I found the number of the frequency of the fines in that class. It's unorganized, like it's not even sorted from smallest to largest, so gross. And I counted them up for you and I found the relative frequency. So I did 1 divided by 50 and I got this, 0 divided by 50 and I got this, yes? What we're going to do in this table is work on the cumulative frequency and cumulative relative frequency. What does that word mean, cumulative? It adds up. Literally exactly right. So a cumulative frequency tells us how many are this class width, this class, or less. To find a cumulative frequency, the first row would say 1, the second row would say 1, the third row would say 8. What am I doing there? Tell me more about adding up. So how many frequencies are in this class? 1. I add this class. I still get 1. I add this one. What do I get?
8.
I add this, so the next one would be
18.
we get it. So 18 responses are this class or less. 23 responses are that class or less. We add up all the way down. Doot, 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 doot. And at the very end, what do you get? This is a good moment to do a quick check. How many fines were in my table? What was my random sample size? And when we add all of them up, what did we get? You should. If you don't get 50 when you're doing a cumulative frequency, if you don't get the sample size, you did something wrong. Now it follows that if cumulative frequency was just adding up the frequencies as you go down the table, what do you think cumulative relative frequency is?
Adding up the relative frequency.
Literally correct. So this is going to be 0.02, 0.02, 0.16. Do we see how this is working? Same exact way. We're telling you the proportion of the fines that were that value or less, because we're adding up the frequencies. What do you get when you reach the bottom of this table? 100% or 1, which makes sense because if this is a proportion of the fines in our sample that are that value or less, all of the values in our sample should be less than the highest or equal to the highest. So we should have 100% or 1 in this last row, or else we put a sad face. So that is just the table version of cumulative frequency and cumulative relative frequency. The ogive graph is on the next page. When you flip that over, we have now displayed this data for you, the cumulative relative frequency, so the proportion of fines that are that value or less, in an ogive. Notice some things about the ogive. One, we have the upper class limits listed on the bottom, meaning that's the largest the fine could be to be in that class. Your first class is from 50 to 75. So this is the upper class limit. I also have a connecting point from all the classes that creates the ogive. And this one in particular is your cumulative relative frequency. So what is the class width of this data? What's the class width? I think I heard it. It should be 25. So if we go from 50 to 75, 75 to 100, 100 to 125, my class width is $25. That's how we're splitting up the different fines. Then we can start reading the ogive. Approximately 80% of all late penalties cost less than what price? Okay. Approximately 80%. Did they give me a value on the x-axis or the y-axis? The y. So here's 80% on the y-axis. We go find the data point that represents that, and what is the fine cost, including late penalties, of that are less than 80%? What? I said that backwards. 80% of all late penalties and fines cost less than what price? $225. You can also read it the other direction. Perhaps it asks what percentage of all fines and with late penalties are less than $200. Well, here's $200. This is the percentage for $200. Yeah, we're going to do an estimate here. What would y'all say percentage-wise that is? I would say 55% personally, because it's about halfway above the halfway point. Between 4 and 6. So we can use the cumulative frequencies to answer questions about things that are less than. I do want you to take a highlighter right now and notice that all of these questions with the ogive are asking for the value of something less than this, because our cumulative frequency and relative frequency are adding up and displaying things that are that much or less than. A quick discussion on official vocabulary here. We've already been using them, but for them to all be officially defined. Classes are the intervals into which data are grouped. When a data consists of a large number of different discrete or continuous data, you want to organize them by classes so you don't have 1,000 bar graphs. To determine your class width, our textbook uses this, formula, which is taking your largest data value minus your smallest data value and dividing by the number of buckets that you want. But then after you do that, you just round to an easy number. So when we do the New York fines one, we took the largest fine, subtracted the smallest fine, and divided by the number of buckets we had. I think I got like 23.5. And do I want to actually split it by $23 each time? No, I made a smart choice and made it 25 as the bucket, as the class width. So you would adjust it to an easy to use value after finding this number. This is an approximate class width. A histogram, we've discussed already. It's a drawing of equal width touching rectangles for each class of data. The height of each rectangle is a frequency or relative frequency. Feels like a bar graph, but it's a little different. Dot plot, you guys got that one. Stem and leaf plot, you guys got that one. Then we have our cumulative relative frequency ogive. It's a graph that shows the aggregate or cumulative frequency for each class. You'd plot points where the x coordinates are the upper class limits and y coordinates are the proportion of observations less than or equal to the category or upper class limit for that data. And then we have our official definitions for our distributions. The first distribution, which we didn't really discuss yet, is called uniform distribution. Notice that all of the distribution, the values here are kind of like literally the same, right? Uniform distribution. There's no bump. Uniform. If you have a bell-shaped or symmetric distribution, there is a bump, and that bump, the highest frequency, occurs in the middle of your data, and you have a tail of essentially equal length on each side. That's bell-shaped or symmetric because it looks like a bell. Then we have our skewed distributions. We talked about this already. A skewed distribution occurs when the highest frequency occurs on one side of the graph and the data trails off to the other side. Your skew, the name of the skew goes in the direction of the tail. So since this one has its most on the left and is trailing off to the right, what would we call this? Skewed right. And since the other one has more of the data on the right and trails off to the left, you would say that this is skewed left. So sorry for the words check your understanding being on this page. I didn't notice that when I pressed print. On the back, we have a few check for understanding questions just to make sure we're all on the same page with these graphical representations. First things first, let's describe the shapes. I like to do this, especially when it's not like a display. I like to actually show the general trend there. It helps me out. What would you call this one? Bell-shaped or symmetrical. The highest one is in the middle and it trails off both sides generally evenly. What about this next one? There's no real bump, right? This one is uniform, which is interesting because I just told you uniform was all the same. These are all generally the same. Ooh, okay, yes, say more. This one is skewed left, very good, because if we were to turn this sideways and look at it as if it was a bar graph, we have more data on the left side. What about the last one? Skewed right, because the tail goes off to the right. Okay, cool, we get the shapes. Here's an interesting stem and leaf plot. This one is called I'm going to highlight this because it's interesting. Back-to-back stem and leaf plot. Sounds exactly like what it is. In a back-to-back stem and leaf plot, we are displaying two sets of data on the same plot. So for instance, if I was looking at this data, I could say that this right here represents the number 6. This represents the number, sorry, did I point at this one? It represents 16 because it's a 1 and then a 6. This number would represent 26. This number would represent 44. So one side looks normal. The other side is inverted going the opposite way. But notice that the numbers this time are going from least to greatest on the inside out. That make sense? Okay. Let's compare the two shapes of the distribution. So this represents the number of grams of fat in 20 different sandwiches served at McDonald's and 20 sandwiches served at Burger King. If we look at the McDonald's one, how would you describe that shape? It would be bell-shaped. It's pretty rough, but if we look at the data we have, not going all the way down to 6, we don't have anything at 5 and 6. We just look at the data. This one is roughly, oh, hello, let me label what I'm doing here. McDonald's is roughly bell-shaped. Okay. And if we look at Burger King, where's the tail? Tail's on the right side this time because our highest frequency is more on the left. So this one would be skewed to the right. What? I just put it to where it looks like a histogram, so where the bars go up. So for Burger King, I flipped it this, you're looking at me, this direction. For McDonald's, I flipped it this direction to make it look like a column. Part B, what is the most grams of fat in any sandwich at McDonald's? McDonald's, the answer is 42. What about Burger King? 68. Nice. So what can we conclude about the two restaurants? Okay, so I liked one of the responses. The response I liked was that Burger King has more high-fat sandwiches than McDonald's. We cannot go so far as to say that McDonald's is healthier because we're just looking at information about the fat content of the sandwiches. I know our brains are trying to make that jump, but what does this data say? This is the only thing the data says because it tells me about fat content, so I respond about fat content. Again, just making sure we can read these sorts of graphical displays. We have question 3 that says a car salesman records the number of cars he sold each week. The frequency histogram shows the results of the car salesman. So the first question asks, how many cars did he sell in the past year? The very first question before we know this, because sometimes we just forget, how many weeks are in a year? Too many. There are 52 weeks in a year. Keep that in mind for later. Notice that this histogram is showing us the number of cars he sold per week and the frequency with which that type of week occurred through this whole year. So let's just look for a moment at our histogram. How many weeks did he sell 0 cars? 4. How many weeks did he sell 1 car? Like, I know we can read this thing, but I just want to see the number for a second. How many weeks did he sell 2 cars? We go down the list. Next one's 8, next one's 12, next one's 8, and then 5, and then 2, and then 1, and then goose egg, that's a 0, and then 10 is 1. So my question for you is, if we're looking at, we can skip this one because he didn't sell any cars. If we're looking at the number of times he sold 1 car, how many total cars did he sell through these weeks?
1.
Well, he sold 1, but how many times did that happen?
2.
So in total, how many cars?
2.
Okay, if we look at this one, how many cars did he sell? 2. How many times did that happen?
18 cars.
So 18 cars he sold. So what I'm doing to figure out how many cars he sold in total in the past year is I'm going to multiply the frequency times the number of cars, because that's what this histogram is showing me. So if I was really showing all of my work, it would be 0 from the first column, 2 from the second, 18 from the third, 24, 48, 40, 30, 14, 8, 0, and 10. That's the number of cars for each week multiplied by its frequency that occurred. If we added all these numbers up, and I would trust you to trust me to add my numbers correctly, we would get 194 cars total. So the frequency histogram didn't just tell you he sold 10 cars, or how many weeks he sold that number of cars. Other things I can ask you from a histogram. What is the most common number of cars sold in a week? 4. What class has the lowest frequency? 9. He sold 0 cars. He sold 9 cars 0 times. And what percent of the time did he sell more than 6 cars in a week? Guess my question for you is, which numbers on here would be more than 6 cars? 7, 8, 9, and 10. How many times did he sell a car? 7, 8, 9, or 10 times? 4 times. Out of how many weeks of the year did he sell more cars than 6? He sold that 4 out of those 52 weeks in a year. What proportion? We are doing a fraction. I would hope you trust me to do this. 4 out of the 52 weeks is 0.077, which means 7.7% of the time this year he sold more than 6 cars. So we can take a histogram and ask you loads different types of questions from them. But you've been looking at charts and graphs and stuff for a while, so I don't think this is anything particularly crazy and new. Let's say we have a different histogram, and this one is hard for you to read, so I'm going to zoom in on it on the screen. It says the frequency histogram represents the number of alcohol-related traffic fatalities by state, including DC, in 2020, according to the National Highway Traffic Safety Administration. What is the class widths used in this histogram? Class widths is how wide each class is. And I know yours is hard to read, so that's why I zoomed in. What is the class width? 100. Which class has the highest frequency? 0 to 100. And then lastly, describe the shape of the distribution. Skewed to the right, because we have a tail on the right. So be ready to answer multiple types of questions when it comes to these displays of data. That's going to be mainly what your homework assignment will have you do.